In this experiment, we explored the changes in acceleration when an elevator moves up and when it moves down. We will briefly discuss why the body feels like it is falling in an elevator going down, and why we feel like the ground is pushing up on us when the elevator is going up.
Okay, so when the object is at rest, you can see here that the force normal and the force of gravity are equal, so then the object doesn't move. But then when the object is accelerating upwards, the vector for the force normal has to be greater than force of gravity. And here, when we are moving down, the force of gravity has to be greater than the force normal.
So while moving upwards in the elevator, the acceleration will be positive, and while moving downwards in the elevator, the acceleration will be negative.
When we started our experiment, we recorded Olivia's mass at rest. We then recorded her mass as the elevator accelerated up and as the elevator accelerated down. We will later discuss what these data points tell us about how the mass is affected by acceleration.
This is my normal wave.
We are now going up. We are now going down.
What?
It didn't change.
That was...
I have a headache.
Okay, so these are the equations that we are going to use in order to find the acceleration of the elevator. Our first equation is force of gravity equals mass times gravity, and force normal, which equals mass times gravity. The gravity in the force normal is opposite in direction as the gravity in the force of gravity. Next, we are going to use the sum of our forces equals mass times acceleration, and the sum of our forces equals the force of normal plus the force of gravity. So therefore, our final equation is force normal plus force of gravity equals mass times acceleration.
Action.
So we are now going to find the force of gravity that we will use throughout the entire experiment, and that remains the same. So our force of gravity equation is force of gravity equals mass times gravity. So force of gravity equals 45.8 kilograms, which is the mass of Olivia, times our gravity, which is negative 9.8 meters per second squared. So we get a total force of gravity of negative 448.84 newtons. So now we are going to find the acceleration as the elevator is going up. So as a reminder, our force of gravity equals mass times gravity, and our force of gravity ended up equaling negative 448.84 newtons. So now we're going to find our force normal as we are going up. So the mass times gravity gives us that. Force normal equals 52.2 kilograms, which is Olivia as the elevator is rising, times our gravity, which is 9.8 meters per second squared. So we get a force normal equaling 511.56 newtons. So now we plug this into our equation of force normal plus force of gravity equals mass times acceleration. So 511.56 minus our force of gravity of 448.84 equals 45.8 times our acceleration. Therefore, 62.72 equals 45.8 times acceleration, and our acceleration as the elevator is going up is 1.37 meters per second squared. So now we're going to find the acceleration as the elevator is going down. So as a reminder, force of gravity equals mass times gravity, and in this case, our force of gravity is negative 448.84 newtons. So now we're going to find the force normal as we are going down, which equals mass times gravity. So our force normal equals 41.7 kilograms of Olivia going down times our acceleration of 9.8. So force normal equals 408.66 newtons. So now we'll plug this in to our equation over here of force normal plus force gravity equals mass times acceleration. So 408.66 equals minus 448.84 equals 45.8 times acceleration. So negative 40.18 equals 45.8 times acceleration, and that gives us an acceleration of negative 0.88 meters per second squared.
Olivia's mass had a slight increase while the elevator was moving upwards. This is because her inertia stayed stationary, which required the force normal to also increase, while the acceleration decreased. According to Newton's second law of motion, which states that the acceleration of an object is directly proportional to both the magnitude and direction of the net force and inversely proportional to the mass, we can further justify that the mass increased while the acceleration decreased. So once again, we can apply Newton's second law to when the elevator is going down. As the elevator moves down, Olivia's inertia prefers to stay at rest, so the elevator and the scale experience the slightest drop. The contact of the person and the scale is essentially reduced. As a result, the force normal is less, and the mass is reduced. So because of Newton's second law, the mass must be inversely proportional, meaning that the acceleration should also increase. In conclusion, our hypothesis is proven correct with the evidence of Newton's second law of motion and how Olivia's mass affected the acceleration of the elevator.